Have you ever paused to consider the vastness of the universe and the countless ways it can surprise us? The cosmos is a dynamic, ever-changing landscape, full of hidden mysteries and events that, while they may seem distant, can have a profound impact on our own solar system. One of the most incredible discoveries made by astronomers in recent years is the realization that our solar system was once visited by a star, an outsider in the vast sea of space, that changed the course of comets and icy bodies in the distant Oort Cloud. A heavenly visitor passing through our neighborhood thousands of years ago may have had a lasting effect on the objects that reside in the farthest reaches of our solar system. But why did this star visit us in the first place? Where is it now? And perhaps most fascinating of all, what can we learn from this extraordinary celestial encounter? In this story, we're not talking about just any ordinary event. We're talking about an encounter with a red dwarf star, Schultz's star, so close to our solar system that it caused a significant upheaval in the orbits of objects within the Oort Cloud, a remote area at the edge of the solar system that we rarely hear about. The Oort Cloud is home to icy bodies and comets that can potentially be catapulted into the inner solar system, and the effects of this star's passing have left scientists wondering just how often such events occur. It turns out that our solar system is far from a static entity, and it's subject to the gravitational pull of stars that might come too close for comfort. In fact, the passage of Schultz's star wasn't just a minor cosmic event, it fundamentally altered the trajectories of certain comets, sending them on paths that could eventually bring them into the inner solar system, and possibly even toward Earth. While this celestial visitor had a surprisingly small mass, only about 0.15 times the mass of the Sun, it was still powerful enough to stir up the distant objects in the Oort Cloud. The star was part of a binary system, meaning it had a companion, likely a brown dwarf, a small, faint stellar remnant that never had the mass to ignite nuclear fusion and shine like other stars. Together, these two objects made their way into our solar system, and their passing caused ripples that may have affected the orbital dynamics of the farthest reaches of our cosmic neighborhood. But why should we care about a faint red dwarf star and its effects on the Oort Cloud? After all, the Oort Cloud is far beyond the reach of our everyday lives. The answer lies in understanding the connections between distant cosmic events and their potential impact on Earth. The orbits of comets in the Oort Cloud are not fixed forever. Over time, the gravity of passing stars can perturb these objects, nudging them into new orbits that bring them closer to the Sun and possibly even into the inner solar system. This could lead to a bombardment of comets, and although such events are rare, they hold the potential for dramatic consequences. If you could turn back time and peer into the night sky about 70,000 years ago, you wouldn't have seen the two Voyager probes that have since traveled beyond our solar system. They hadn't even launched yet. But you might have seen something else, a bright red spot in the sky. This was not a trick of the imagination or the result of light pollution, which, admittedly, is worse today than it was back then, but rather the dazzling appearance of a visitor from another part of the galaxy, Schultz's star. At that time, the sky would have looked a lot more vivid and clear compared to what we see now. The dazzling red light in the sky would have been visible to our ancestors, who lived through the Stone Age, a time when there was no artificial light to obscure the stars. What's truly fascinating is that this stellar visitor, although it seems small by comparison to our Sun, played a far more significant role than scientists first realized. When researchers first identified Schultz's star in 2013, they initially dismissed the idea that it could have had a major influence on the solar system's architecture. After all, red dwarfs are typically quite faint and have relatively low mass. With just 0.15 solar masses, Schultz's star seemed like it couldn't possibly cause much disruption. But the closer astronomers looked, the more they realized they might be wrong. The real mystery started to unfold when astronomers noticed something peculiar about the star's motion. Although it was located just 22 light-years away, which is relatively close in galactic terms, Schultz's star seemed to be barely moving in relation to our solar system. This was an oddity in itself, and there were two primary theories to explain the star's movement. Either it was headed directly toward the solar system, or it was leaving the Sun's gravitational influence and moving away from us. To figure this out, scientists used the star's spectroscopic data to analyze its motion and pinpoint its exact trajectory. The findings were nothing short of amazing. Using advanced computational models and data from the star's trajectory, astronomers were able to work backward in time and determine that, around 70,000 years ago, Schultz's star passed through the outer reaches of the Oort Cloud. In fact, it passed so close to our solar system that in 98% of the simulations run by scientists, the star went directly through the Oort Cloud, causing an unprecedented level of disruption. This was no minor occurrence. The gravitational influence of Schultz's star would have caused some of the icy objects in the Oort Cloud to shift their orbits and possibly enter the inner solar system, and even come close to Earth. At first, scientists were skeptical. After all, the star's small mass made it hard to believe that it could exert enough gravitational force to disrupt the Oort Cloud so dramatically. But the data didn't lie. The effects were undeniable. And while the direct impact of this disruption on Earth remains unknown, scientists suggest that it may have triggered a series of events, sending icy bodies from the Oort Cloud on paths that brought them closer to the Sun. The result? A possible increase in comet activity, which may have had profound effects on the solar system, including on Earth. It's possible that our planet may have experienced an uptick in comet impacts as a result of this close encounter. The idea that passing stars could perturb the Oort Cloud and send comets into the inner solar system is not a new one. It's a hypothesis that has been around for decades, but for a long time, there wasn't any evidence to support it. Schultz's star, however, seems to be the first confirmed example of a star passing close enough to significantly influence the Oort Cloud and its contents. But what makes this even more compelling is the fact that there are likely more such visitors out there. The universe is vast, and stars move throughout the galaxy on different trajectories. Some may come closer to our solar system, while others may pass far beyond our reach. But the story of Schultz's star teaches us that these stellar encounters can have lasting effects on the structure of the solar system, including its distant parts, like the Oort Cloud. For now, Schultz's star has passed beyond our solar system and is currently located around 22 light-years away. It's unlikely that we'll have another close encounter with it, but the discovery of this event opens up a new chapter in our understanding of the forces at work in our solar neighborhood. However, the story doesn't end there. There's another star on a collision course with our solar system, GLE 710. Unlike Schultz's star, GLE 710 is not a faint red dwarf. It's a star with a mass of about 0.6 solar masses, which means it has more gravitational pull and could cause even more disruption if it passes too closely to the Sun. Currently, GLE 710 is still about 62 light-years away, but in roughly 1.3 million years, it's expected to approach the Sun to within 1.1 light-years, a significantly closer distance than the 0.8 light-years at which Schultz's star passed. When GLE 710 gets closer, it will likely stir up the Oort Cloud, sending icy bodies on new orbits that could increase the frequency of comet impacts within the inner solar system. The potential danger is not limited to just comets. The increased frequency of cometary impacts could present a greater risk for Earth, especially if one of these objects were large enough to cause widespread destruction. While the likelihood of a catastrophic impact is still low, the fact that these events are more likely than we once thought is cause for concern. NASA's DART mission, which demonstrated that it's possible to alter the trajectory of an asteroid through targeted impact, provides a glimpse of how we might be able to deflect potential threats in the future. But for now, we can only speculate on the possible consequences of this future encounter. The lesson we can take from the passage of Schultz's star, and the potential encounter with GLE 710, is that the solar system is far more dynamic than we tend to think. It's not a perfectly stable system, it's subject to the gravitational influence of distant stars, and as we've seen, even small stars can have a significant impact. It's a reminder that space is full of surprises, and we can't predict everything that might happen. Our place in the universe is more fragile than we often realize, and understanding the forces at play in the cosmos helps us better understand the history and future of our solar system. So, what can we learn from this cosmic story? First and foremost, we are reminded of how interconnected the universe is, and how events happening millions of years ago could still have an impact on us today. The passage of a star through our solar system is a reminder that the universe is full of unpredictable forces. It challenges our understanding of what's possible and encourages us to keep looking to the stars, as they may have more to teach us than we think. As for now, we can only wait and see what other mysteries the universe has in store for us, and keep an eye on the stars, both near and far.